Okay, so this is our math video, and my name is Megan, and I did the growth equations.
My name is Hannah, and I did the decay equations, and we are period 4.
So this is our linear growth equation, and as I read the equation, I'm going to be circling important parts of it. So Jessica is dog sitting for her neighbor CJ. CJ has one dog named Lucky. CJ has to pay Jessica a starting amount of $10, and for every time she visits, it's $5. So on this slide, there's our table and our equations. So the starting value is 10, as you can see in the recursive rule and explicit rule. And the recursive rule is next equals now plus 5, and the start is 10. And the explicit rule is y equals 5x plus 10. On the next slide, I'll be showing you the graph. Okay, so here is the graph, and on the x-axis is the number of visits that Jessica made to CJ's house, and here is the amount of money that Jessica made for every visit on the y-axis. And it is a linear line because it is a constant rate of $5 for every visit. In this slide, I'm going to be showing you how to solve the first prediction. So, if Jessica visits Lucky for 10 days, how much money will she have in total? So I did 3 times 10 because she visits Lucky 3 times every day for 10 days, and that equals 30 visits. And then the explicit equation is y equals 5x plus 10. So you're going to plug 30 in for x because that's the amount of visits. So y equals 5 times 30 plus 10. And that equals 160. So she will get $160 after 10 days.
Okay, so next we're going to do the linear decay problem. And I'm going to be underlining important numbers as we go along. And so the question is, Tom is trying to lose weight. He's currently at 300 pounds, and his goal every week is to lose 4 pounds. And on the next slide, we will be looking at the equations and the table. And this is our table in 2 equations, and it starts out at 300 pounds at 0 weeks, and then he loses 4 pounds each week. And then our equations, the first one is the recursive rule, and that is start equals 300, and then next equals now minus 4. And then the next equation is the explicit one, and that is y equals negative 4x plus 300. And then after this, I'm going to show you the graph. Now you are going to see our graph of the problem, and as you can see on the x-axis, it is the weeks, and then on the y-axis, it's the weight, and it starts at 300 and goes down at a constant rate of 4. In this slide, I'll be showing you our exponential growth problem.
Write what I said.
And I'll be circling the important parts. So Alex is a turtle researcher. He researches the patterns of reproductions for turtles in North America. In 2000, they started with 100,000 turtles, and every year the population doubles. So in this slide, you're going to see our table and our equations. So in year 2000 or 0, it's 100,000, and it doubles every year. And so as you can see, our recursive rule is next equals now times 2, and the start is 100,000. And our explicit rule is y equals 100,000 times 2 to the x power. And we'll do our predictions on the next slide. In this slide, I'm going to be showing you how to solve our first equation. So, in what year will the turtle population exceed 10 million? And so right now, I'm just pulling up what I typed, what came up into our calculator after we typed in our explicit rule, which is y equals 100,000 times 2 to the x power into y equals. And as you can see, between 6 and 7, or 2006 and 2007, it exceeded 10 million. In this slide, I'm going to be showing you how to solve our second prediction. And it's how many turtles will there be in 2010. So the way I solved this was I did our explicit equation, which equals y equals 100,000 times 2 to the 10th power. So first I replaced x with 10 for year 2010. And so I solved what 2 to the 10th power was, and that equals 1,024. So now you do 100,000 times 1,024, and that equals 102,400,000 turtles in 2010. In this slide, I'm going to be showing you the graph for the last equation I just showed you. So on the x-axis is the number of years, and on the y-axis is the turtle population. And as you can see, the line is curved because it's an exponential growth.
Next, I'm going to show you the exponential decay problem, and that is overfishing of tuna is a worldwide issue. In Europe, the population in 2002 was 750,000. Every year, the population decreases by 30%. Now I'm going to show you our table in equations. And as you can see, in year 0, aka 2002, it is 750,000, and it decreases by 30%. In our recursive rule, it is start equals 750,000, and then its next equals now times 0.7. And then our explicit rule is y equals 750,000 times 0.7 to the x power. And it's 0.7 because you have the full population before, and then so that is 100%, and then you minus it by 0.30 because that is the decreasing, so that equals 0.7. Okay, now I'm going to show you our first exponential prediction, and that is if the tuna population continues to decrease every year, how many tuna would there be in 2010? And so first I wrote our equation out, and that is 750,000 times 0.7, and I replaced x with 8 because 2010 is 8 years away from the start, which was 2002. And then I solved the equation, and I got 43,236 tuna. Next, I'm going to show you our second prediction, and that is, in what year will the tuna population go below 10,000? And as you can see in the calculator, at year 12, which is right here, it is at 10,381. But at year 13, it is at 7,266. So that is when it will go below 10,000. And I got that by typing my equation into y equals in the calculator. Now I'm going to show you our graph of the problem. And as you can see, on the x-axis, it has the years, and then on the y-axis, it has the tuna population. Now, as you can see, it decreases, and the line is at a curve because it's an exponential decay.